Okay, welcome to this lecture. We're gonna prove the Urysohn Metrization Theorem, and we're finally here. Okay, so we're gonna need 3 lemmas to finish our work before our proof. And the first lemma states that any countable product of R is metrizable. And I have this result in a separate video. I will put the link in the description. And also another lemma is that if Y is a metric space and X is homeomorphic with Y, then X is also metrizable. Okay, so the proof is easy. Simple. So we first give a homeomorphism, and then we define a matrix on X in such way. Okay, so the distance between X and Y and X is the same as the distance of them and Y under the map F, because F is a homeomorphism, and we define such as such. And this is can easily check as a matrix on X, and we show that. And we also have this equality, and the proof is here. Okay, we have this equality. Now, we first give the origin topology on X and the metric topology on X. We want to show that they're equal, which is precisely means that X is metrizable. So first, let U open a metric topology on X. Then for X and U, we can pick an epsilon X such that is in U, right? It's centered at X is in U because U is open in metric topology. Now we apply F on both sides. Gives this and subset of F of U, right? So we have this. Now this means that for any element in F of U, right? For any element in F of U, there, right? For X and U, Fx is in F of U, right? For any element in F of U, we can find a radius such that this is true. So F of U is open in Y, right? Y is a metric space, right? Y is a metric space, then U is a pre-image under a continuous map, right? Or of an open set. So U is open in X. Now, suppose that U is open in X, then Fx and Fu is open in Y because F is a homeomorphism. Now we pick, right? Because this is open, we can make some choice, which means that, right? This is an F of U, which means that we apply F pre-image, gives this is true, which means so X and U, we can find epsilon X such that this is true. So U is open in metric topology on X. Yeah, so we basically proved that. We basically proved this fact. Okay, so with these lemma, and we have one more lemma. This lemma is a bit more complicated. So for any X that is regular and second countable, then there exists a countable collection of continuous functions such that for any X and for any neighborhood U of X, there exists a Fn such that at X naught it is positive, and outside of this neighborhood it vanishes. And the existence, first we know that a second countable regular space is a normal space, which means that we can apply Urysohn lemma. Okay, so let's apply Urysohn lemma. For any X naught in any neighborhood U of X naught, we know that such F exists, right? Such F exists. But we have to cut down the size to a countable collection. So now the condition of second countable comes in. We first give a countable basis of X, and for NM such that this is true, we can apply Urysohn lemma, right? Such that on this closed set is equal to 1, on the other closed set is equal to 0, right? We can separate two closed sets by a continuous function. And now we just apply this. We apply this, right? We fix an element X naught and any neighborhood U of X naught. Okay, now we can pick a basis, right, as this. Now, because X is regular, again, we can pick a neighborhood, right? We again get a neighborhood of X naught, right? So we can pick a neighborhood V of X such that V bar is in like a BM, Now again, for this v, right, for this neighborhood v of x, we can pick another basis Bn such that this is true, right? Thus, Bn bar Bm, right? So Bn bar is in Bm, which means that on x naught, right, is equal to 1, and on x subtract u, which is because we have this, so we have this, right? Which means that this is actually equal to 0, right? Okay, so it is, and since we also know that this collection is indexed by a subset of a countable set, which is countable. So yeah, this lemma is also proven. Okay, we have this. Now we're gonna prove the Urysohn Metrization Theorem. If it's regular and second countable, then you are metrizable. Okay, so let's just prove it. So the idea is that we embed x into a subspace of the countable product of the closed interval 0 to 1. And this is a metrizable space, right? Because R is metrizable, R omega is metrizable, and this is a subspace of a metrizable space. So this subspace is also metrizable, right? So let's say the metrizable space is metrizable. And we give the countable collection of continuous function in the lemma which is stated above. So we give this countable collection of function. So remember their properties, okay? Remember their properties. Now, we take this with the product topology, okay? We take this with the product topology. And we take this with the product topology and we define a function from x to 0, 1 omega as fx is f1, f2, blah, blah, blah. F1, f2, f1, f2 are the collections from the lemma. Okay, so we have this, and this f is the embedding we want. So let's just verify. Because we're given with a product topology, and each component function is continuous, so f is continuous. And f is also injective because for any x not equal to y, we pick a point x in the neighborhood of x, right? Because t1, so this point is closed. So we pick a point x in the neighborhood of x. For any point x and for any neighborhood of x, there exists a fn such that it is positive, right? And it vanishes on x subtract this neighborhood, which is this, right? So fx is not equal to fy because there's a n such that they differ. So f is injective. And third, we have as a function, as a function from x to its range is a homeomorphism. So basically shows that f is embedding. And first we let z denote as the image set, okay, fx. So this is a subspace, right, of this, and we show that f is an open map. So we want to show that every point u open in x, we want to show that f of u open in z. Okay. This is what we want to show. So first, we pick u open in x. For x naught and u, denote f of x naught as z naught, okay? And we already have a point in the neighborhood, so we can separate it, right? Pick fn such that fn at x naught is positive, and on this is 0. Now we want to define V equal to the preimage of the projection map. We let V be a sub-basis element from 0 to 1 omega, and we let Wx0 be this open set intersect with Z. So this is eventually open in Z. Okay, this is open in 0, 1 omega, right? Because this is open in 0, 1. Right, this set is open in this. Okay, so we let this is open in Z. And firstly, we have this Z0 is in W because, right, pi n of x0, pi n of Z0, which is equal to fn x0, which is positive. We already have this, right? And this is contained entirely in f of u. Why? Because for any z in this set, first of all, you're in Z, which means that you're in the image set. Second of all, you're in V, which means that, right, which means that pi n of Z is positive. Pi n of Z is positive. Now, pi n z is equal to what? Fn of x. Fn of x is larger than 0. But recall we had this, which means that x must be in U. And if it's not in U, then 0 greater than 0, right? So x must be in U, right? So z equals to fx, where x is in U, so z is in f of U. So we have for any x not in U, we had a w x naught such that it is in f of U, which contains a neighborhood, it was a neighborhood that contains f of x naught. So f of U is the union equal to the union of such set, and each of them is open in Z, which means that f of U is open in Z. So we're done, right? Surprisingly, we're done. Okay, so but I'm not feeling enough, right? I want to do more math. So we want to give another version of the proof, but in order to give another version of proof, we have to recall something. So recall that given any index set for x, y, and rj, we define the row bar metric as this. This is the uniform metric. This is the uniform metric. Recall this is the uniform metric. Okay? And rj with the uniform metric topology is finer than the product topology on rj. And this is the proof. So we have this is true. So we have x is equal to some point, and we have a basis containing x. And we pick finally of them that is not equal to entire space, and for each of them, because they're open in R, right? They're open in R, right? So we can just pick, the standard topology on R is metrizable, and D bar, the metric topology they generated are the same. So for each of them, we can pick an epsilon I such that this is true, right? For each x alpha I, right? You could pick an epsilon I such that the ball is containing U of I. Now we just make epsilon be the finally of them. We pick the minimum. Then if rho bar xz is less than epsilon, so if z is in this ball, right, then by definition, for any alpha, each of them must be less than epsilon, which precise in particular for those different from R, we have they're all less than epsilon, and right here we done. So z is indeed inside this. So what we've done is, what we've really done is we have this is true, right? So the product, the metric topology actually finer than the product topology, right? Pick any point in any basis containing x, right? We can find a ball that is still containing x. So the metric topology is finer than the product topology. Okay. So now we're going to give a second version of the proof. So for this second version, we're going to embed x into a subspace of 0, 1, omega again with the uniform metric rho bar restricted on this, right? The restricted rho bar on, because, okay, rho bar is defined on Rj, right? But now, what I'm saying, this with rho bars is actually the restricted metric, right? But remember, the restricted metric is the same as the substrate topology, right? Right. And we also it's really the same as this. Okay. So notice we have this. Now, first, to prove it, we give a countable collection, blah blah blah, and we can also require each of Fn is less than or equal to 1 over n. Right. We can just scale each 1 over n Fn to make this true, right? So now, remember this is important, and we define the same as before, and as above, injectivity, the proof is the same, but the proof of open map is different. So here's a side note. So this is my side note here. My side note here is that, okay, for any T prime topology on X such that T prime is finer, then for the subset Y, and this is the substrate topology inherited from T, and this is substrate topology inherited from T prime, then we have, this is true. So what I mean here is that since the metric topology on this is finer than product topology on this, so the metric topology on this is finer than the product topology on this. And the product topology on this is really just, let me go to the lecture of product topology. Remember, we have this theorem. For a subspace of X alpha, product of the subspace, right? The product topology of each subspace is equal to the subspace of the product topology. Right? So the rigorous reasoning is here, combined with this, right? You have to pause and think about this, right? It's some detail that if you don't be careful, you won't notice what is happening at all, right? The metric topology on R omega is finer than the product topology on R omega, so the metric topology on this, which is basically the subspace, right, is finer than the product topology on this is the same as the subspace topology viewed as a subspace from the product topology on R omega. Okay, so all in all, this one sentence, which means that F is an open map, because for U open in X, we know that FU is open in F of X, right? But F of X is a subset of this with the product topology as above, right, in version 1, right? And we using this again. Right? If F of U is open in F of X, all right, and F of X is viewed as a subspace of this with product, but because this with rho is finer than the product, right? As right, since again also since also we have the metric topology on this is finer than the product of this, right? So if you think about in subspaces, right? So f of u is open of f of x, where f of x is viewed as a subspace of this, but this with the metric topology. Okay, so we have to be clear in our topologies. Okay? So f is an open map. It's an open map. Okay, it's an open map. Now, we show that f is continuous. So this is going to be different from the component-wise, because in component, we're equipped with product topology, so we can do that, but this is the metric topology. We have to prove it in a way of metric. And to prove it, first, for example, epsilon greater than 0, we want to find neighborhood u such that this is true, to show that f is continuous. We pick n such that 1 over n is less than epsilon over 2 by Archimedean property, and as f is continuous, right, we have this is true. So we let u be the intersection of those un's. So if x is in u, if we're less than this, we have this, right? The exact same thing. If we're greater, since fn is a function from x to 1 over n, right? So any 2 points, its difference from must be less than 1 over n. Thus, the supremum, right? The supremum, right? Remember we have this, right? Over 2, right? We have this, it's less than epsilon. So we're done. Okay? And in the both versions of the proof, we actually see something. So here's the theorem. If x is a T1 space, right? Like we see something in terms of this big F, right? And notice the theorem is that if x is a T1 space in the collection, any collection of a continuous function, such that for any x, for any neighborhood u of x, there exists an f alpha such that this and this is true. Then this function f from x to rj by this embeds x into rj. In particular, if it's to 0, 1, then f embeds x into 0, 1j. And the proof is really just replace n by alpha, right? I mean, or more precisely, 0, 1 omega and 0, 1 j. Okay. So here's a remark. We see that if x is completely regular, then any collection from above exists, right? Because x is completely regular, right? So we're good with this. We're good with this collection, right? Conversely, such collection exists, which shows that x is completely regular. So this gives a corollary that x is completely regular if and only if x is homeomorphic with the subspace of this. And the proof is again by a little few words, right, which I'll skip. Okay. So yeah, the most important thing is the Urysohn Metrization Theorem. Okay. So I'll end this lecture. Okay, I'll see you guys next time.